Good day, everyone. For our this week's topic, we are now on week number 6. Okay, we are now on midterms, and for the first topic of our midterms, we have the signal flow graph. Okay, so in our past discussions, we discussed about amplifiers, gains, the different types of amplifiers. Okay, so now we will look at the system in a holistic way. Uh, Yeah, realistic way. Okay, let's start. For the learning outcomes of this material, so by the end of this module, a student will be able to, number one, understand the basic elements of signal flow graph. Number two, construct signal flow graphs. Number three, convert block diagrams to signal flow graphs. Okay, so that's it. For the topics, we have basic elements of signal flow graph, construction, and then conversion of block diagrams to signal flow graphs. Okay. For the basic elements, nodes and branches are the basic elements of a signal flow graph. Okay. Anyway, we're talking about signal flow graph. As I've mentioned, our previous topics, we're talking about gains, signals, amplifiers. Okay. So, signal flow graph is a good diagram so that we can see what is happening to our signal. So from the input, it will pass through different stages. It can be amplifiers, it can be filters, and so on and so forth. Okay, so the signal flow graph gives us a good idea on the different stages that our signal will have to go through. Okay, so the node is a point which represents either a variable or a signal. There are three types of nodes: the input node, the output, and a mixed node. Right. So this is the definition. The input node is a node which has only outgoing branches. So from the input node, it can only go out. The output node has only incoming branches. Signals can only come in on our output node. For our mixed node, okay, it has both incoming and outgoing branches. Okay. For example, let us consider the following signal flow graph to identify these nodes. Okay, so we have here a signal flow graph, and we will have to identify the different nodes in this graph. Okay, when we say nodes, uh, as you can remember from your circuits, right? Nodal analysis, KCL, KVL, whatever. So a node, we usually represent a node with a dot, uh, and it is between elements. Okay? In a signal flow graph, the node itself is the element. Okay? In this case, these are nodes labeled here y1, y sub 1, y sub 2, y sub 3, and y sub 4. Okay? So the signal will have to pass through these different nodes. So you can see, by the definition of our nodes, we have input node, the signal can only go outgoing, or the branches are only outgoing from the input node. The output node, the branches can only go in or ingoing to the output node. Then we have mixed nodes wherein uh, branches or signals can go in and out. Okay? So identifying the nodes here, we have y sub 1, y sub 2, y sub 3, and then y sub 4. Y sub 1, we only have an outgoing branch. Okay? This signifies the direction. Direction, direction. We only have an outgoing branch. So therefore, y sub 1 is an input node. Y sub 4, we only have here a coming, incoming branch. So y, we can say that y sub 4 is an output node. Y sub 2 and y sub 3, in this case, okay, there's an incoming branch to y sub 2 and there's an outgoing branch from y sub 2. The same with y sub 3. Incoming branch, outgoing branch. So y sub 2 and y sub 3 are mixed nodes. Okay? So this one. The next element here in our signal flow graph is a branch. A branch is a line segment which joins two nodes. We have two nodes, a line, that is a branch. Okay? What information can we get from a branch? It has both gain and direction. Okay? So the name or the label for our branch signifies the gain. Okay? In this case, you have branch A, branch B, branch C. Whatever the value of A, of B, of C, and of D is the gain. Okay? So from Y sub 2, the signal will have gain A before entering Y sub 2. From Y sub 2, the signal will have a gain B. Okay? Before entering Y sub 3. Then from Y sub 3, the signal will have a gain C before entering Y sub 4 and a negative D gain going back to Y sub 2. Okay? Now, uh, this must look whatever to you. So, to give you a good example, I'm actually using a repeated example since the previous meeting, right? Previous meetings, okay? So we have here a, let's say, a microphone. So it is a wired microphone. Okay. Then from our microphone, it will pass through what we call a preamp or preamplifier. Then from our preamp, it will go through our main amplifier. Okay. So for those who are familiar with audio systems, I'm sure you can relate to this example. Then from our amplifier, we will now go to our speaker. Okay, so uh, that's how usually an audio system is. Did I draw a speaker or a face? Let's take this as a speaker. So we can say that if we will call this y1, y2, y3, what is this writing? If we call this y1, y2, y3, y4, okay. Each stage, okay, will have a certain gain moving forward, okay. So from our microphone, we can only speak on the microphone. The microphone does not produce sound. So therefore, the signal is only incoming to the microphone. Who is the input, by the way? I did not include the input. So the input here will be the uh, human being or whatever that is speaking on the microphone. It will say some words. What is this? Is this words? It will make a few sounds. Okay, into the microphone. So the microphone now will receive the signal. Okay, then um, should we include the person? I don't think we should include the person. Okay. The electronics starts with the microphone. So microphone will be Y sub 1. Okay. This is an acoustic signal hitting the what's the term again? Usually these are carbon. Depends on the structure of the microphone, of course. So the most common one are carbons. There are carbon part molecules, particles in here. Okay, that vibrates as we speak, and then the level of voltage that will be the output or current that will be the output of the microphone depends on the vibration of the components inside. Okay, so from this one, there will be a signal going out. Of course, it will not be a one-to-one conversion from the acoustic wave. Okay, there will be some amplification, even though it's very small. Okay, then from the preamp, the signal will enter to the preamp and it will amplify the signal to some degree. Okay? Then, going out of the preamp is an de-amplified signal. Now, we label that amplification B. From the preamp going to the amplifier, of course, the signal again will be amplified. Okay? So the signal now that will go out of the amplifier is not B, but another amplified signal called C. We call it C. Okay? We don't have a returning signal in this example. We'll just go with a linear example here. Then, on the speaker, there will be no amplification that will happen because it will convert this electrical signal to acoustic signal that the human ear can hear. Okay, so this is an example of um, signal flow, actual signal flow that can be represented using our signal flow graph. Okay, so I hope that's clear. That was clear. Let's go back to the presentation. Here we have an example. Let us construct a signal flow graph by considering the following algebraic equations. Okay. We have here, instead of a system, we are given algebraic equations to represent our signal flow. Okay, so let's try to understand what does this expression means. First, we have y sub 2. Okay, y sub 2 is equals to a 1 to y sub 1, or a sub 1 to y sub 1 plus a sub 4 to y sub 4. Okay, now this is the sum of these signals. Okay, going back to our previous example, remember that, let's say this one, y sub 3. Y sub 3 is equal to the signal going to y sub 2 times b, because b is the amplification of the signal that will enter y sub 2. So we can say that y sub 3 is equals to b times y sub 2. Okay? So in this case, y sub 2 is actually a node, and the signal that should enter node y sub 2 should be equal to this signal. Okay? Remember from our previous topics that we refer to gain with A, okay, and A. So this must be gain. But aside from the letter A, of course, the analysis is that this is paired or multiplied with a node, so therefore it must be the gain. Anyway, proceeding. So y sub 2 is a signal from y sub 1 multiplied by A going from node 1 to node 2. Let's try to follow along with this one. Okay, let's make a what? That's so cute. Anyway, from the equation, there was a sub 4 2, so meaning at least 4 nodes so far. Okay. So y sub 2, let's call this y sub 1. Yep. Y sub 1, y sub 2. This is where the 4 came from, y sub 4. So there must be y sub 3, of course. And then y sub 4. Okay, maybe we can lower down the names. Or, yeah, lower down the names. Anyway, again, y sub 2 is equals to the gain 1, 2, meaning from 1 to 2 times y sub 1. So, the signal from y sub 1 going to y sub 2 times the gain a sub 1, 2. Okay, so let's see. I just assume that 1 sub 2 or the sub for A. Since all gains are labeled A, these numbers must mean, or not really must, more likely to mean uh, nodes. Okay, so from node 1 to node 2. Next, the signal from Y4. And the gain is from node 4 to node 2. So it will jump from node 4 to node 2. Okay, so this one. And notice that you might be wondering earlier with the negative gain. Okay, notice that the ideal situation is for our signal to flow from input to output, right? To have the maximum gain. But there are cases or there are devices that what they do is they return the signal to a previous stage, or they revert the signal back to a previous state. So what happens is, if you will put it in the signal flow graph, it looks like it goes back to the previous direction like this one. So if that's the case, we will label it negative. What does the negative means? It means instead of flowing from input to output, the signal is flowing back to the input. Okay? Why is there a case like that? It is usually feedbacks. Okay? So we have also discussed feedback in the previous topic and in your previous courses as well. Feedbacks are signal which are returned to the uh, to some stages of the flow so that it can compare the output. Okay? So if in an ideal state there will be flow in here and then there will be flow in here, right? So this is input, this is the This one is the output of this stage. This one is the output of this stage. This one will be the output of this stage. Now, uh, before it goes to the output or the main output, there will be stages that will check if the system is doing fine or doing great or doing its job correctly. Okay, so to do that, they will have to sample the signal from the output stage and then analyze it back on the input stage. Maybe compare it to the input if it's still similar or if it is doing as intended. So those are feedbacks. Okay. Example of feedbacks. Uh, Air conditioning units. Okay. Let's say you have set your air conditioning units to 26 degrees Celsius or 24 degrees Celsius or 18 degrees Celsius. Now, the air conditioning unit can't just simply uh, blow up cold air. Okay, it has to measure the temperature of the surrounding. Okay, now in the case of air conditioning units, when it measures the temperature as still greater than 18, so it will continue to produce cold air. Okay, now when it starts to measure 17 degrees Celsius, so the output is now not as intended. The intended output is 18. When it starts to measure, let's say 17, 16 degrees Celsius, it goes back to the input or to the system and say, hey, this is not equal to 18. What should we do? It will stop producing cold air. Okay? Now, when it starts, it stopped, right? Now, when it starts to measure that it's getting higher than 18, let's say, oh, it's now 20 again. Go back to, so that signal will be feedback to the system and say, hey, we are above the as intended. So it will blow or it will produce cold air again and so on and so forth. So that's the purpose of feedback. So this one here is more likely a feedback signal. Okay, that's why we have reverse directions in our signal flow graph. All right, next. So we're done with our y2. So y3. Y3 is equal to the gain from node 2 to node 3 times y sub 2. Then the gain from node 5 to node 3 times y sub 5. So we have y sub 5. We have to add another node. The most ideal way here is to check first all of the equations to see how many nodes should we do. But in my case, I just want to show you the step-by-step process. So I'm doing it one by one. Anyway, I've deleted this one. We added it earlier as just an example. Y sub 3 is equals to A or gain from 2 to 3 y sub 2. Gain 2 to 3 y sub 2. Okay. So from y sub 2 times gain 2, 3. We also have another signal which is A53 or the gain from node 5 to node 3 times y sub 5. So this is y sub 5. So gain from node 5 to node 3. Okay, so A 5, 3. Again, reverse direction, negative. Okay. We good with this? I hope we're good with this. Let's proceed. Y sub 4 is equals to the gain from node 3 to node 4 y sub 3. Okay? So y sub 4 is equal to the gain from node 3 to node 4 y sub 3. So this is gain 3, 4. This is y sub 3. Then y sub 5 is equals to a 4 5 y 4, or the gain from node 4 to node 5 plus the gain from node 3 to node 5 y sub 3. We have a jumping signal here. This is node 4 to node 5, a 4 5. Then from node 3 to node 5, a 3 5. So the jump is not only on the uh, reverse direction, it can also bypass some nodes. Okay. Lastly, we have another node. We have to add another node. That's why the most ideal step is to place all the nodes first and then see the directions. But again, I did it one by one, just to show you the step-by-step process. Y6 is equals to the gain from Y5 times, or sorry, the gain from node 5 to node 6 times Y5. So this one, A5, 6. So this is our signal flow graph from the given equations. Okay. So again, as we can see, from y sub 1, we have only one outgoing signal. So y sub 1 is the input node. From y sub 6, we only have incoming signals. So y sub 6 is the output node. Okay. Breathing time. Okay, let's proceed. There will be 6 nodes. Yeah, we've already done it. There will be 6 nodes and 8 branches. So 8 branches. 1, 2, 3, 4, 5, 6. Okay. So this is the step-by-step process as we've done. Oh, anyway, okay. It did not denote it as negative. So I guess we have to wait for it to call it negative before we say negative. Okay. So we'll follow the example for now. It did not call the signal negative, so we will not. So I guess unless stated, it will not be referred to as a negative signal. Anyway, another reason why we have negative gains is that, for example, we have this type of amplifier. There are amplifiers that works like this. Okay. If the signal input, or if the input signal is like this one, the output signal is inverted, amplified and inverted. Okay. It's the same signal, but it was inverted. Okay. I think this is the work of an inverting amplifier. It has its pros and cons, of course. But the major pro of this is this has less distortion as compared to the non-inverting amplifier. This is the most common amplifier that is being used. Anyway, as you can see, the input has or the output has a different orientation from the input. So the gain here is negative because the orientation of the output is different. Anyway, let's proceed. So if this is not negative, meaning the orientation, I guess, is the same. It's not inverted. That's why it is positive in here. So, and yeah, I think that's the reason why. Let's proceed to the next topic. We have the conversion of block diagrams to signal flow graphs. So to convert a block diagram into its equivalent signal flow graph, so we have to follow these steps. So one, represent all the signals, variables, summing points, and takeoff points of block diagram as nodes in signal flow graph. Represent the blocks of block diagram as branches in signal flow graph. Represent the transfer functions inside the blocks of block diagram as gains of the branches in signal flow graphs. So I hope you still recall how our block diagrams look like. Okay, so these are our block. This is an example of our block diagram. So again, these are some of the steps. Uh, let's identify first again. These are the gains. These are the blocks and block diagrams. These are the gains. Okay. So after the gains, sorry, device, output, gained output, device, gained output, and so on. So in between gains, there should be a node. Okay. Nodes, nodes, node, 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 and node, and node. Okay. Then the blocks again are the gains and the label or how the label of the gain or the value or the magnitude of the gain depends on the label of the blocks. Okay. Then we will follow the direction as stated or as seen on our block diagram. We have two more steps, I guess. So these are three. Connect the nodes as per the block diagram. If there is connection between two nodes, but there is no block between them, then represent the gain of the branch as 1. For example, between summing points, between summing point and takeoff point, between input and summing point, between takeoff point and output, and so on and so forth. Okay, so these are summing points, in between gains, in between gain and summing points. Okay, intersection of gains, summing points. See, should we do it here? Yeah, we should do it here. So we have 9 nodes. Okay, we have 9 nodes. Two, three, 4, 5, 6, 7, 8, 9. Okay. This will be y sub 9, y sub 8, y sub 7, y sub 6, y sub 4, y sub 3. Okay, y sub 1, y sub 2, y sub 3, y sub 4, y sub 5, y sub 6. Pardon my handwriting here. Missing mouse. Y sub 8 and then y sub 9. Okay. Then the input signal is RS. RS. This is our input signal. This will go to Y1. Then from Y1, we have two signals. Incoming to Y1, we have our RS, or the input, and then a feedback from the node 8 with the gain of H2. Okay, a feedback from node 8 with the gain of H2. Next, Y2. There are two incoming signals on Y2. That is the signal from Y1, we have no gain, and then signal from Y4 with a gain of H1. As stated on the steps earlier, if there is no stated gain, or we have 2 points and there is no gain between them, or we have two nodes and there is no gain between them, uh, more likely, or the case is, the gain is 1. Let's it again. On y sub 2, we have a signal from y1 with not no gain, gain of 1, and then y sub 4 with the gain of h sub 1, so 1, 2, 3, 4. You have here a signal with the gain of h sub 4. Ah, h sub 4. Okay, h sub 1. Where did they get h sub 4? Anyway, this is h sub 1 supposedly. Then next, on our y sub 3 or node 3, on our node 3, from y sub 2, we have a signal with the gain of G1, a gain of G1. Then, on our y sub 4, it will be a signal from y sub 3 with the gain of G2. I think the easier way here is to make a larger circle, and then the labels of the nodes should be inside the circle, so that we can avoid confusion. In my example here, the labels are below. Might be hard for you to see. Okay. So I guess in your part, when you do signal flow graphs, do a larger circle and then put the label inside the circles for your nodes. Let's proceed. Y sub 5. Y sub 5 is a node beside Y sub 4, so the gain is 1. And also a signal from Y sub 9 with the gain of H3. A signal from Y sub 9 with the gain of H3. I think we should avoid overlapping signals when making our diagram. To avoid the confusion and to have a better aesthetic on our output. So H sub 3. Now, even though the answer is correct, but if the output looks very, 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 very messy, it's really hard to look at. Okay, Y sub 6. So from Y sub 6, it is beside a summing point. Again, it was stated in the direction. So the signal is from Y sub 5 and a gain of 1. Next, we have Y sub 7. We have two signals incoming to y sub 7. That is the signal from y sub 6 with the gain of g3 and also a signal from y sub 6 with the gain of g4. So both from y sub 6. Okay, g3 and g4. Okay. Next, from y sub 7 to y sub 8, so they are beside each other, summing point. Okay, so we have a gain of 1 between them. Then from y sub 8, that will be a signal to y sub 9 with a gain of g5. Okay, so that's it. This is our signal flow graph from the given block diagram. So let's see if our answer is correct. Okay, so this time some of the feedback signals were labeled negative and the gain 1 is stated. How do we know? Sorry, I forgot what my sentence was when I said how do we know? Yeah, I was trying to say how could we know if the signal is negative? In the case of block diagrams, it is actually easier to identify if the signal should be negative or not. Okay? For examples, y sub 1 is a summing point. Both signals are positive. Okay? Y sub 2 is a summing point. The signal from y sub 1 is positive as stated in the block diagram. And the signal from y sub 4 is negative. That's why h sub 1 should be a negative. I forgot this part. And then, let's see if we also have other negatives in here. This one, both positive, so no problem. This one, we have a negative signal from y sub 9 to y sub 5 with the gain of h3. So h3 should be negative. So let's check our answer again if it's the same. Now, negative h3, negative h1, gain of 1, gain of 1, gain of 1. Okay, now I've also overlooked another thing. R sub s, again, is the input. And y sub s is the output. Of course, they are nodes. Come on. They should be nodes. So R sub s going to y sub 1, no gain yet. So gain of 1. Also y sub 9 to y sub s, gain of 1. In block diagrams, input, output, they should also be considered as nodes. Okay? Okay. So that's it. This is our signal flow graph from the given block diagram. Okay? So that's it. That's our lesson for this week. So it's all about signal flowgrams.